In order to find the magnetic field of a long straight wire, we're going to set up a coordinate plane system with a current carrying a charge I is lying on the x-axis, with the current moving in the positive x direction. In order to find the magnetic field at point P, which is a distance d away from the wire, we're going to first determine which direction the magnetic field will be pointing. So using the right hand rule, you can point your thumb in the direction of the current, and your fingers will wrap in the direction of the magnetic field. So at point P, the magnetic field will be coming out of the paper. With this information and with the coordinate system we've established, we can figure out the magnetic field using the biot-savart rule, which states that the constant mu naught times 4 pi times the current times delta S cross product r hat over r squared is the magnetic field. To apply this to our our long straight wire, which we will assume is infinitely long, we need to break the wire into small segments of delta Q. Each delta Q has a small amount of the charge and a small portion of the length of the wire, delta X. So using this information, we can start to plug in these values into B to find the magnitude of the magnetic field. Starting with the cross product of delta S r hat, we find out using our diagram that delta S cross product r hat is equal to delta X, which is the small length of the part of the wire we are looking at, times 1 for our r hat, times sine theta k. Since the cross product breaks into the product of delta S and r sine theta, and the angle is between the r hat and the direction of the current. So using this, we can plug that back into our equation. Now we can solve for our r squared. Now the radius, or the distance from our small amount of charge to our point, I label as rk. And this is equal to the square root of d squared times plus xk squared, according to the Pythagorean theorem. Next, we can plug that back into our equation. And since r is squared, the square root is canceled out. Next, we can solve for sine theta k. So looking back at our diagram, we see that this angle, theta k, we can find in terms of d and xk by looking at how this angle relates to this larger angle. So this smaller angle between rk and the x-axis is 180 degrees minus theta k. So sine theta k is equal to sine 180 minus theta k, which is equal, using trigonometry, so SOHCAHTOA, so sine is opposite over hypotenuse, so it will be opposite d over rk. And in the previous step, we found that rk is equal to square root of d squared plus xk squared. So we can plug that in for our k. So that is our quantity for sine theta k. So we can plug that back in to our formula over here. Next, we can just do some simplifying. So this, forgot that there, excuse me. So this term and this term can be combined. So we have d squared plus xk squared to the power of 3 halves. And so this is our magnitude of b in the k direction, which is a vector representation of the z-axis. So this is the magnitude. Now we just have to figure out, this is the magnitude of the small section of the wire here. Now we have to integrate it in order to determine the magnitude of the wire, of the magnetic field caused by the entire wire. So in order to do that, we integrate from negative infinity to infinity our formula over here. So mu naught I d delta x over 4 pi d squared plus xk squared to the 3 halves. And then when we're integrating, we're going to use delta x to represent our dx. So we can pull out the constants. Which are mu naught id over 4 pi integral from negative infinity to infinity of 1 over d squared plus xk squared to the 3 halves dx. Now this integral is rather complex, so you can just use the integral table found in the back of the book, which tells us that this integral is equal to the constants times x over d squared square root d squared plus xk squared, evaluated from negative infinity to infinity. Now when you plug infinity and negative infinity into the integrand, you get which simplifies to then you can cancel here and here, so that your final answer is mu naught I over 2 pi d. And that is the magnitude of the magnetic field caused by a long straight wire. And having previously used the right-hand rule, the direction would be in the positive z direction.